All right, everybody. Today we're going to be going over the basic chemistry notes. This is the inorganic chemistry. You've probably had this, at least in part, at some point in middle school. But this stuff is really important for you to really understand what we're going to talk about next, which is the organic chemistry, which is really specific to biology. So I'm just going to kind of go through these notes really quick. And then you'll be working on the macromolecules activity. And you're only doing pages 1 and 2 of that activity. So if you run into issues on that, refer back to these notes. You can use your book, obviously the internet. So all of those things are open to you. So when we're talking about chemistry, we're talking about elements, and elements are found on the periodic table, which I know all of you are probably familiar with. Elements are made up of atoms. So one of the biggest issues I see, this is even in honors chemistry when I taught that, is really understanding the difference between an element and an atom. I always told my students that elements are like the team you play for. So like, the Chicago Bears or the Chicago Blackhawks, and the atoms are the players that play for that team. Now, we'll kind of get into that more down below. But in terms of biology, you've probably heard that organisms are, carbon-based life forms, and that's the pencil. That is not what I wanted. Carbon-based life forms. So obviously carbon is a major element found in the human body, but you also have combinations of nitrogen, hydrogen, and oxygen bonded with that carbon. The reason carbon is so important to life is because carbon actually has 4 spaces for bonding, which allows it to bond in several long chains, which can create all of the macromolecules that are really needed for life. But we're going to get into the macromolecules next time. Again, this is just a lead-in. There are other elements that your body needs, and these are called trace elements. And these are things that a lot of times you see, like on the back of a label. Calcium, phosphorus, potassium, sulfur, iron, iodine is examples given there. You might take like a multivitamin that has those in there. So you need them in very small amounts, but you pretty much get them in all the food you eat. Let's talk about the next section is really kind of looking at the differences between compounds and elements, and they are very different. A compound is basically a combination of atoms bonded together in a very specific ratio. So, for example, H2O is a compound. Now, in order for it to be a compound, you have to have 2 different elements present, right? So, like, oxygen gas would not be a compound because it's only made of oxygen, so that would be elemental, right? So we have to move that one down. So this would be an element. Okay, so you can obviously have multiple atoms bonded together to be an elemental substance. The key there is that compounds have to be more than one element. Another example would be something like salt, NaCl. Okay, we talked about with digestion, hydrochloric acid, that would be a compound. So anything that has more than one element is called a compound, and they're in very specific ratios. So obviously, if you have a glass of water, for example, you don't just have 2 hydrogens and 1 oxygen in that whole glass. But if you had, a million molecules of that water, you'd have 2 million hydrogen atoms and 1 million oxygen atoms because it's a 2-to-1 ratio. So, and that's true for every molecule of water. An element is a pure substance. Compounds, obviously, because they're made up of 2 different elements, are not considered a pure substance of only one type of atom. And the properties and characteristics of elements are fixed, and not necessarily the same as the properties and characteristics of the compound after. So, for example, you've got H2O here. I'll put another element example. So hydrogen gas is H2. So hydrogen gas and oxygen gas, if you put those two things together, that's explosive, right? I mean, I think most of you have heard of the Hindenburg. That's an explosive combination. But obviously, water is not flammable; it's not explosive. So, even though hydrogen and oxygen individually are flammable, water, when you put them together, they lose that property. So, characteristics. This is kind of what this is talking about here. The characteristics of the elements don't necessarily translate into the compound itself. Okay. Let's talk about atoms now. So the smallest piece of an element is an atom. And I told you that they're kind of like the players of the team. So like if you've got the hydrogen element here, there are different players of hydrogen. Now, what that means is if you play for the team, that means that the protons of all of these players, so if this is player 1, this is player 2, all playing for team hydrogen, player 3, they all have the same number of protons. That's what puts them on a team. For hydrogen, it's 1 proton, okay? So all these guys would have 1 proton. Now, does that mean they're all the same? No, because some players can have 0 neutrons, and hopefully, you've heard of these before. Using symbols here, this is a P plus because protons are positive, neutrons are neutral. Some hydrogen atoms will have 1 neutron in their nucleus, and some will actually have 2 neutrons. And each of those, even though they're all hydrogen, they're hydrogen because the number of protons is 1, they all belong to this element. They're all the same element, but obviously they're different individually. They have a different mass. To figure out the mass of these things, you would just add these two things together. So the mass of this first player would be 1, and the mass is measured in atomic mass units. The mass of this one would be 2 atomic mass units, and the mass of this one would be 3 atomic mass units. Now, each of these individual players does have a name. It's called an isotope. That's kind of going beyond what we need to talk about. Just trying to remember if I put that in our notes at all. Yeah, we didn't. But just to kind of a little bit of a foreshadow to what you're going to learn next year. And one of the biggest things that students really struggle with is this concept, is that you have the same element, but you have 3 different atoms, and these 3 different atoms are called isotopes. So those are the individual players. In this class, you're really not going to have to worry about that too much. But let's kind of go through an atom now. It's a very basic level. We already talked about protons. Protons have a +1 charge per proton. Neutrons are neutral, so we use a 0 for that. And electrons are negative. Okay. Protons exist inside the nucleus. Now, the nucleus of an atom is a little bit different than the nucleus of a cell. The nucleus is just the center of the atom, right? Whereas the nucleus of a cell obviously can move around. It's a little bit different. Now, that is going to be the same as that one right there. Okay, neutrons are also located in the nucleus. And finally, electrons are located in orbitals. That's getting, again, a little bit too deep. We'll say that they're located in the rings around the atom. These, of course, around the nucleus, I'm sorry. These, of course, it's a little ambiguous. Don't think about, like, in terms of rings like rings around a planet, or the planets obviously orbit around the sun in a very specific single plane. These rings go all over the place, and actually they're more of a cloud. And that's why sometimes the electrons are said to exist in the electron cloud. I'm sure you've probably seen I'm sure you've probably seen pictures of an atom, right? And it kind of looks like there's the nucleus, and then you've got like rings going all kinds of different directions like that. That is actually not really correct, because that's very much like a solar system. It's known as the Bohr atom. In a real life atom, you've got the nucleus, and then you've got a haze that exists around the nucleus, and that haze is where the electrons exist. So they're kind of zipping around all over the place out here. And that's a little bit more correct of how an atom would look like if we could see one. No one ever has, of course. So there's that. The periodic table, I'm sure you've had some experience with the periodic table. You're going to learn a whole lot more about the periodic table when you get into chemistry. For our purposes, it's organized by atomic number. So this is atomic number 1, this is atomic number 2. Now this actually is a little bit confusing because this is something you'll learn next year, but hydrogen is actually kind of out of place. It really should be there, but it has to go here because of its valence electrons. I'm not going to get into that, but that's why that's there. But then this would be 3 and 4 and so forth, and you could barely see that, 5, 6, 7, and so forth. Okay, it's organized by atomic number. When you do that, it's also, so like, why don't we just put it one big straight line, right? Or why is there this huge gap here? Why is there a huge gap here? And the reason is because there's other properties that we use vertically. So the metals are all grouped together. The non-metals are all grouped together. There's these grouped right here, right along this kind of black line. This is the metal non-metal line. This border right here. The atoms that are around that are known as metalloids. They kind of have properties of both metals and non-metals. But where are the metals located? They're located in the lower left side. I mean, obviously it's a huge area. This is all the metals there. And then the non-metals are top right. This kind of talks about like why hydrogen's out of place. Obviously hydrogen is a non-metal, so it should be over there. But again, you'll learn more about why it's there in chemistry next year. Hydrogen basically has it can't figure out if it wants to be a metal or a non-metal, so it has properties of both. But again, you'll get into that next year. What is the exception? The exception are those metalloids. Oh, actually, maybe the exception, actually, I think we're talking about here is hydrogen, even though I told you I wasn't really going to get into that. It's the reason it's an exception. Again, I don't want to get into it too much, but it basically acts as a metal sometimes in reactions. But obviously we know that hydrogen is a gas, right? We know hydrogen gas, so it's not a metal, but in reactions it does sometimes act like a metal. All right, when you're looking at individual boxes in the periodic table, obviously you can't see them here because this is a very basic periodic table, but you've got several different things inside. At the top, a lot of times it's at the top left, but it can be at the top right, is the atomic number. This is the number of protons. Going to move this, make this a little smaller so it's not in my way. There you go. So this number up here is the atomic number. This is atomic number is the number of protons that are in an atom, and this is really what determines the element, like we talked about before. 1 is hydrogen, 2 is helium, 3 is lithium, 4 is beryllium, 5 boron, 6 carbon, 7 nitrogen, 8 oxygen, 9 fluorine. Reason I kind of go through those, I guess chlorine to be another important one, but those are the ones that you're really going to find inside the human body. So the element symbol is just a symbol. A couple things about the element symbol to keep in mind. The first letter is always capitalized. The second letter is always lowercase. So when you're looking at something like HCl, this always, sometimes students are like, is this HCI? No, it's HCl. That's a lowercase l. You have to be really specific. So like when you do iodine, you definitely want to draw your I like that because it can be a little confusing with that L. But these are little tips for chemistry next year. The element name follows below that. And then what's below that is what's known as the atomic mass. Now, this can be a little confusing because it's a decimal. The atomic mass is actually a weighted average. Of the mass number of all of the different isotopes that exists. Okay, that's why it's a decimal, right? So I mean, there are no lithium atoms that have a mass of 6.941. That doesn't make a lot of sense when I already told you the mass is determined by the protons and neutrons, right? So these are all whole number masses. You can never have a decimal place. But when you start dividing all of the isotopes, remember these are isotopes of hydrogen, for example. Okay, so there's some that have 0 neutrons, 1 neutron, and 2 neutrons. It's a weighted average, so we have to look at like how much of each of those individuals there are. That's how you get a decimal place. Now, where it says here proton number equals electron number, that's in a neutral atom, all right? So if there's no charge, if you're talking about a lithium atom, it's going to have 3 protons. It's also going to have 3 electrons because those are opposite charges, so they have to equal each other. Now, that doesn't always happen. Sometimes you'll have what's called a lithium ion, and you'll see it has a 1+ charge. Right? That means it has 1 more proton than electrons, right? Now remember, lithium has to have 3 protons because in order that's what makes it lithium. So that would mean lithium 1+, the ion, would have 2 electrons because it would have 1 less electron than protons, giving it a 1+ charge. Another one that you'll see pretty often in biology is calcium. Calcium has a 2+ as its charge. So that means it has 2 more protons than electrons, okay? All right, moving down. Counting subatomic particles, the number of protons is done by the atomic number. That's always the case. The number of neutrons differs between isotopes. There's that word again. Isotopes are the different players. So how do you know what isotope you have? Well, you're not going to really run into this in this class, but like you may have heard of something like carbon-14. You may have heard of that because that's the element, that's the radioactive element of carbon that we use to figure out the age of long lost living things. That's how we know like the age of a dinosaur bone, for example. Carbon-14, if we know that carbon has 6 protons, right? 14 is what's known as the mass number. And that is the exact number. That's not a decimal. That's the exact mass of carbon. So that means there are 8 neutrons in that, right? So when you have the mass number, you basically, you know what the protons are because it's carbon. So you would look that up on the periodic table and you would notice that carbon has an atomic number of 6, okay? Its atomic mass is actually 12.01. This tells you that carbon-14 is actually not a very common isotope because if I round the atomic mass, it would be the most common would be carbon-12, right? 6 protons and 6 neutrons. But regardless, the mass number is the exact mass of the isotope you're talking about. And it's always given when we do an isotope name, which is what carbon-14 is, the mass number is always the number that follows the element name, okay? Number of electrons in a neutral atom will always equal the number of protons. That's what we talked about above. Unless you have an ion is an atom with a charge, okay? Atom with a charge. And that charge is always put to the top right of the symbol. So like if we had chlorine as an ion, it would have a 1 minus charge. So that tells you it's 1 minus. That tells you it has one more electron than protons. Okay, so we already did the lithium 1 plus. Let's do went way too far. Let's do something like fluorine. So fluorine, actually let's do oxygen. So oxygen, when it becomes an ion, has a -2 charge. So you'd have to go and look up oxygen's atomic number. So if you did that, you look at the periodic table, oxygen looks like this. It has atomic number of 8. It has atomic mass of 16.01. It's actually, I think sometimes it's 15.9999. I've seen that too. Just depends on the periodic table you're using. So if we take that, we know that it has 8 protons, right? Because the atomic number is right here. That has to be the same because it's oxygen. But it has 2 more electrons than protons. So this number can't change. I can't go like, this is what I see a lot. Students are like, well, it has 8 electrons. It must have 6 protons. That would be wrong because that means it wouldn't be oxygen anymore. It would be carbon. That can't, so the number of protons can't change, but the number of electrons can. So if the number of electrons can change, I can bump this up to 10 electrons. And that is how you figure out number of electrons. You take the charge, you take the atomic number, you know the atomic number equals the protons, and then you just have to kind of use a little bit of logic. Obviously, you can use some mathematics as well, but there's 2 more electrons than protons because it's a negative charge and electrons are negative, so we have 10 electrons. To figure out the neutrons, again, we would have to give you an actual mass number. If we didn't give you a mass number, then you assume you have the most common mass of oxygen, which would be 16. Okay, so if its mass was 16 and 8 protons make up oxygen, that means it has to be 8 neutrons to get to 16 as a mass. Okay, the electrons don't count because the electrons are so small they don't actually have a mass that contributes to the mass of the atom. All right, so what's the importance of electrons? If obviously they don't count toward mass, why do we even worry about them? Well, because it's the atoms that actually determine the bonding of the atom. Atoms want to follow what's called the octet rule. That means that they prefer, so octet rule, I'll write it out here. They prefer to have, think oct, 8 electrons in their outermost shell. There are some exceptions to that, but that's what they want, okay? And they're going to either gain or lose or share electrons to get to that 8 in their outermost ring or their outermost energy level. All right, so atoms fill their electron shells at the lowest energy level first, closest to the nucleus. Electrons in the highest energy level are known as valence electrons, and this affects the reactivity because, again, it's that outer shell that we care about, the highest energy level. If the outer energy level is partially full, and again, partially full means less than 8. There are some exceptions. I'm not going to get into that here. Then the atom will react with other atoms and form bonds to fill its outer energy level. If the outer energy level is full, then the atom is what we call happy. Happy means stable, means non-reactive in that state. It says right here. And will not react. Okay. So how does it get there? Well, there's a couple ways that atoms that are not stable can get to that octet rule. If you have basically 2 nonmetals, when they bond together, they share electrons. So real common example is H2O. Carbon dioxide would be another one. So hydrogen and oxygen, both nonmetals. Carbon and oxygen, both nonmetals. They're going to share electrons. Ionic bonds happen between a metal and a nonmetal, right? So like you could have calcium chloride, CaCl2, One of the more common ones, sodium chloride. Don't use something else other than chlorine here. Let's do aluminum fluoride. There you go, AlF3. Okay, all right. Moving down, hydrogen bonding is very important in biology. This happens due to something called polarity. Polarity is when you have an unequal distribution of charge. If you notice, the hydrogen atoms here have a slight positive charge. This because they're very small and they're sharing their one electron. So their one electron is being shared with oxygen, which means that it gets pulled toward the oxygen, and that leaves basically these little protons out here all by themselves and makes that side slightly positive. Because the electrons are being pulled toward the oxygen, that makes the oxygen, since electrons are negative, slightly negative. When you have this situation, and this happens really easily in water, you basically get what's called a hydrogen bond. Now, it's an attraction between different molecules. The hydrogen of one molecule is attracted to the either fluorine, oxygen, or nitrogen. It's those three. It has to be those three setups in order to get a hydrogen bond of a different molecule. So, for example, methane, CH4, would not have hydrogen bonding because that's not fluorine, oxygen, or nitrogen. Okay, so H2O is really the one that we really look at. I'm struggling right now. There we go. Is really the ones that we look at because water is obviously, our bodies are made up of mostly water. Most biological systems are water. So we see a lot of hydrogen bonding with water. If you take a look here, here's a water molecule. I always call it the Mickey Mouse molecule. Okay, oxygen is the face. The ears are hydrogens. Remember, the ears are positive. So this hydrogen is going to be attracted to the oxygen of another water molecule. That, because their opposites attract, you get a force of attraction there, and that force of attraction is called a hydrogen bond. Remember that we saw hydrogen bonding in DNA. There's no water there, but there is nitrogen because you've got the different nitrogen bases. So it's basically oxygen bonded to nitrogen causing those hydrogen bonds. Describe some of the properties of water. So you've got solubility, and this is due to things being dissolved by water. Water is called the universal solvent. The solvent is what does the dissolving. So it's called the dissolver. The solute is what's being dissolved. And water, because of its polar nature, in biological systems is the dissolver in almost every biological system. Hence why it's called the universal solvent. Other properties of water: cohesion. So this is how water sticks to itself. We see that with, just in hydrogen bonding above. Like there's cohesion, right? Water sticking to itself. One water molecule is attracted to another water molecule. What do we see in like everyday life? Like how do we see cohesion? If you've ever filled like a glass of water where it actually goes above the glass of the water and kind of hovers there, that's an example of cohesion. If you've ever seen like a water droplet form, like if you ever see like water droplets like rolling down the glass and they actually come close to another water droplet, you actually see it like go bloop, and it's almost like a little magnet. It sticks together. The other property of water we talk about is adhesion. Adhesion is the property of water where water sticks to other things. To non-water substances. So the fact that I just said, when it rains and water is stuck to glass, like sometimes those raindrops are literally stuck there. They're not falling due to gravity. So obviously there's an attraction between the water and the glass. This attraction, if you actually come up with a really small tube, if you've ever had, remember to the doctor where they take like a blood sample and they poke your finger and then they stick a little tube to your finger, and the blood goes whoop right up the tube. That's because, of course, blood is mostly made up of water. And when you use a small tube, it's called capillary action. And this is how water can climb up a small tube without any exterior force, right? Capillary action is also how plants' roots work. So, a plant isn't like literally sucking water up into its roots. It's actually capillary action that's doing that automatically. All right, in terms of bond strength, of the ones we've talked about, covalent is the strongest. So they're the strongest. Second is ionic bonds. And then last is hydrogen bonds. Okay? So hydrogen bonds are really, really weak. We talked about, when we talked about like DNA and DNA replication, the reason DNA unzips down the middle is because of those hydrogen bonds. They're very, very weak. So they're able to pull apart very easily. Obviously super important in terms of biology. All right. On this next page, it just shows you a whole bunch of different pictures, just kind of showing like diagrams of ionic bonding. What I want to show you about ionic bonding, so ionic bonding is when electrons are transferred. I don't think I highlighted that when I talked about it, but electrons are transferred from the metal to the nonmetal. If you look here, sodium has one valence electron. Okay, it has one electron out there. Remember, it wants 8. So it could either try to gain 7 or it can try to kick out 1. So metals kick out because they always have very low numbers of electrons in their outer shell. Non-metals, notice chlorine has 1, 2, 3, 4, 5, 6, 7. It wants 8, so it either could gain 1 or kick out 7, because remember there's a shell underneath it that is full. So obviously it's easier for it to gain 1, so these two become partners, and sodium will donate that electron over to chlorine, and over here you can see now they're happy, stable, but now sodium has lost an electron. That gives it a positive 1 charge, where chlorine has gained an electron. There's sodium's electron right there. So it is now -1. And because of that, positives and negatives attract to one another. So there's a force of attraction that pulls these two atoms together, and they stick together and form salt. Okay. Covalent bonds, neither of these really want to give up electrons, but what they can do is they can share electrons, and at any given moment, either of them would then have 8. So they can't donate them, because then they would each be giving up 1, they'd be down to 6. It doesn't work that way. But if they can come together and share, so here, I'll do 2 different colors here. Let's say that this color, oh, I forgot to count, 1, 2, 3, 4, 5, 6, 7. Those aren't very equally spaced, but there's the 7 that the one on the right had. If I change colors now, 1, 2, 3, 4, 5, 6, 7. That was done a lot better on that one. You can see that now if I count the electrons around the chlorine on the left, there's 1, 2, 3, 4, 5, 6, 7, 8, right? So it has 8. And if I count the electrons for the right one, 1, 2, 3, 4, 5, 6, 7, 8, and now they're both happy. And because they're sharing this pair right here, that's the bond. That's a covalent bond right there. Okay, the last image here is hydrogen bonding. So I think this right here, that picture is fantastic, just showing all the different types of bonds. The rest of these, again, these are just more examples of that. This is some more biological examples with macromolecules. We're going to cover those a little bit later. Here's another example of covalent ionic bonding there too. Okay, but you can look those over. You have them in your notes. They're there to help you kind of understand this whole concept. And that's where we're stopping. Our organic chemistry notes will be on Friday. Hopefully I'll be back in school, so I'm obviously feeling not so great. Hopefully this is maybe the end of this rather than the beginning, even though I just started feeling like this yesterday. But hopefully it's a quick one, and I'll be back on Friday. I'm sure I will be, regardless if I feel good or not. And hopefully all goes well. So now what you're going to do is go ahead and open up your macromolecules activity. Pages 1 and 2 are the only pages you have to do. Do not turn it in because we're going to finish that on Friday. So please do not turn it in early. And I'll see you Friday.